Imagine training an AI agent that must think, act, observe, and adapt across many steps, not just answer one question. Now here's the problem. Traditional reinforcement learning only gives feedback at the very end. It's like teaching a student with only a final exam score, but no corrections during the learning process. This paper introduces SDAR, Self-Distilled Agentic Reinforcement Learning, a new method that teaches AI agents more intelligently during training itself. Modern AI agents operate in long, multi-step environments. Every action changes the future context, and because of that, small mistakes compound over time. Previous methods like OPS tried to help by giving token-level supervision from a teacher model. But in multi-turn environments, this becomes unstable. The student slowly drifts away from the teacher trajectory, and eventually training collapses. The researchers discovered something important. Not all teacher signals should be trusted equally. If the teacher strongly agrees with a token, that's useful guidance. But if the teacher disagrees, the disagreement may actually come from noisy retrievals, bad skills, or multi-turn drift. So blindly copying the teacher can hurt learning instead of helping it. So SDAR takes a different approach. Instead of forcing the student to imitate every teacher token, it introduces a gating mechanism, a dynamic filter. Each token decides how much supervision it should receive. Helpful teacher signals are amplified, uncertain or harmful signals are softly reduced. One of the most important design choices in SDAR is that reinforcement learning remains the primary optimization engine. The distillation component is only an auxiliary helper. This preserves the stability of reinforcement learning while still injecting fine-grained token-level guidance. To validate their approach, the researchers tested SDAR on 3 major agent benchmarks: ALFWorld for embodied decision-making, WebShop for online shopping agents, and Qwen for search-augmented reasoning. They evaluated across multiple Qwen model families, including Qwen 2.5 and Qwen 3. Here's how the system works. The agent interacts with an environment and generates trajectories. A privileged teacher branch receives additional skill context. Then SDAR compares teacher and student probabilities token by token. Finally, a sigmoid gate determines how strongly each token should influence learning. SDAR also introduces skill retrieval mechanisms. The system can retrieve structured demonstrations or action templates from a skill library. These skills help guide the teacher branch during training. The researchers even tested multiple retrieval strategies, including keyword matching, UCB retrieval, full retrieval, and random retrieval. The reinforcement learning component is based on GRPO. The model samples multiple trajectories, evaluates rewards, and updates policies using clipped policy optimization. This ensures stable RL training while avoiding extreme policy shifts. At the heart of SDAR lies a key metric called the teacher-student gap. This measures the difference between how confidently the teacher and student predict the same token. Positive gaps indicate valuable teacher guidance. Negative gaps indicate uncertainty or potentially harmful supervision. To control this process, SDAR applies token-level gating. A sigmoid function transforms the teacher-student gap into a smooth confidence score. This creates adaptive supervision. The model learns where to trust the teacher and where to ignore it. The paper experiments with 3 gating strategies. Entropy gating focuses on uncertain tokens. Gap gating prioritizes teacher-endorsed tokens. And soft-OR gating combines both uncertainty and disagreement signals together. The results are impressive. Across ALFWorld, Qwen, and WebShop, SDAR consistently outperformed baseline reinforcement learning methods. In some tasks, gains exceeded 10%. Most importantly, SDAR avoided the catastrophic instability seen in naive OPS approaches. This is significant because long-horizon AI agents are extremely difficult to train. Tiny mistakes compound over time, and unstable supervision can completely destroy learning. SDAR introduces a safer and more adaptive way for AI agents to learn from privileged knowledge. One fascinating discovery was skill internalization. Unlike methods that require external skills during inference, SDAR actually absorbs those skills into the model weights themselves. That means the final agent performs better, even without external guidance. The researchers also found that SDAR generalizes better across different environments and model sizes, especially on smaller models like Qwen 3 to 1.7b. SDAR dramatically outperformed other hybrid training methods. During training, the gate activation ratio changes dynamically. Early on, many tokens are suppressed because the teacher signals are unreliable. But as learning improves, more tokens become useful and the gates activate more frequently. Even more interesting, SDAR remains robust even when retrieval quality is poor. Amazingly, even random skill retrieval still improved performance over pure reinforcement learning. This shows that the gating mechanism effectively filters noisy supervision. The paper also performs extensive ablation studies. Gap-based gating performed best among all strategies. The researchers also discovered that overly aggressive distillation harms performance, while moderate guidance works best. Another key finding involves the choice of divergence objective. Reverse KL divergence significantly outperformed forward KL and Jensen-Shannon divergence. Why? Because reverse KL focuses learning on the strongest teacher-supported modes, instead of spreading probability mass everywhere. This work builds on the growing field of agentic reinforcement learning. Modern agents are no longer static chatbots. They browse websites, use tools, play games, automate GUI, and interact with environments over long horizons. The paper also advances on-policy self-distillation. Previous OPST methods struggled with instability and rigid scheduling. SDAR replaces those hard-coded rules with adaptive token-level supervision. The authors even provide mathematical proofs for stability. Their analysis shows that the gated objective behaves like a weighted likelihood optimization, while strictly bounding gradient magnitudes. This helps prevent exploding updates during training. The sigmoid gate is actually a crucial innovation. Without it, teacher-student mismatches could generate massive unstable gradients. The gate smoothly controls learning intensity, creating a self-paced curriculum at the token level. SDAR represents a broader shift in AI training philosophy. Instead of rigid supervision, future AI systems may learn through adaptive trust mechanisms, where guidance is dynamically filtered rather than blindly followed. This could have major implications for future autonomous systems, from AI copilots and robotics, to web agents and scientific discovery systems. Stable long-horizon training is one of the biggest unsolved challenges in modern AI. So in summary, SDAR combines reinforcement learning with adaptive self-distillation. It selectively trusts teacher guidance using token-level gating. It improves stability, performance, and generalization while avoiding the collapse seen in earlier approaches. AI agents are evolving from simple assistants into autonomous decision-makers, and methods like SDAR may become foundational for training the next generation of intelligent systems. The future of AI may not just depend on bigger models, but smarter learning itself.